This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, we'll make a start. Just before we start, tomorrow I will have got the assignment 2 brief on LMS, and I will talk you through the brief tomorrow as to what you need to do. Is that all right? Talk about the assignment tomorrow. Assignment 2 is very straightforward, so that's why you should. I didn't say that. I said the first one was not hard, but tricky. You need to spend some more time. Assignment 2, I have to say that it's easier to do if you come to the site visit. That's why it's compulsory. And if you don't come to the site, you'll not be able to answer the questions, unfortunately, because there are certain information not given in the brief that you have to get from site. And we'll talk about a bit more. So what we're going to cover today, continuing from last week, we'll look at steel structures. We're going to continue on that, which continues into portal frame structures, steel portal frame. So it's all the same linked topics or lectures. And what we used last week is very, very important to understand the properties of the materials, how the steel structures behave, and you use a lot of that knowledge to use for your assignment, as well as what we're going to cover today and tomorrow. And next Monday, we're going to site, which is in Truganina. The first bus departs here at 12:10, so we get to site at 1. It's about a 45-minute bus ride, and you have fun on the bus. We make fun, we laugh, and have lunch on the way. Okay. Is it provided? No, that's not part of the You can ask Robert or Valerie for that. Okay, so we're going to look at steel portal frame structures. So this basically looks at typical structures, which are portal frames, which like the typical burnings that we have in Australia, because they are warehouse sort of style, and which sort of look like that, which you would have seen. So we look at all of the elements, look at how they behave, especially under wind, how they are built, how they are put together, some of the factors you need to consider, and so on. Okay. So for today, continuing to tomorrow, today we're going to look at these various elements of steel portal frame. We'll look at the layout, loads, how it's laid out, and how load impacts on them. We'll look at the roof and wall sheets, purlins, and then bridging. I've got some models here for you to see, so we'll talk as we go. So as always, we've got all the reference materials on the side there if you want to make some reference. So I think I explained this last week when you have a portal frame. So a portal frame is one that has got usually 4 joints. So it's got 4 joints, which is 1, 2, 3, 4. So that's one portal frame on its own, if that makes sense. Okay? So usually you will have either a pin connection. So a pin connection, I think I demonstrated that. It's on the circle and open. That's a pin joint, which means, what is a pin joint? What does that mean? Yes, but there is an important, doesn't take moment, yes, so it doesn't transfer. That connection doesn't transfer or transmit a moment from one member to another. So that's why it's a pin, that's why you see it deflects a lot, and then you'll have rotation at that connection as well. Whereas if you have a fixed one, which is like that, okay, you have 2 portal columns and a portal beam, or you call that a rafter as well, it's the same thing. When it's like that, it shows that it's a moment connection. So as you can see, that's a 4-pin. Usually it's unstable, so that is why we don't build like that, because if it's pin, 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 you push it over, the structure will just fall down, and you don't want that to happen. Otherwise, you go to jail. So what we do then is to sort of provide bracing. So that's why we have either bracing in that form, which is like what you will see when we go to site. So luckily for us, the site we're going to go, the structure is already been built. This frame, I mean the steel portal frame, is already almost finished. According to the manager, they are doing now the roof, and then they have put in some precast. So you're going to see a lot. Unfortunately, you will not be able to see the industrial slab, which is done at the end. So we'll see a lot when we go onto site. So you can have a 4-pin joint as well. So pin, 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 pin with one strut like that. Or you can have one with a 4-pin and one stiff panel. So that might be like a precast panel, for example, a concrete. Usually infill panels are expensive because it's more laborious. You have to build piece by piece. So that's why I use a precast panel. So that stiff panel might be a precast panel, which if it's quite low, for ones that are usually about 8 meters high, they usually use a precast, full precast panel. The one we are going to has got precast panel and has got wall sheeting. So it's two different materials you have used. So you see all the guards, how it's been installed. You see all the other elements which we'll talk about today. Okay? And then, as I said, you can have a stiffer one, which is pin at the base, but stiff or rigid at the connection, which is what is very typical of what you will have in a portal frame construction. So most of the structures built will be like this, in this frame. This one is very expensive because you've got two fixed connections, and that usually is not done. It takes some time as well. Now, for most of the structures, as I said, you'll have a rigid knees. The knees are rigid, which is the beam to column connection. At the ends, these are rigid, so that's the knee there. You'll have, I'll show you as we go along. And usually the base are pinned. So it becomes a very simple fabrication. So usually what happens is the connection at the base will have very, very minimum amount of bolts. So when we go to site, we'll try to see this. I've looked at the drawings, and they all are built like that. And at this stage, because the structure is exposed, so you'll get to see sort of like the naked fabric. So this is what a portal frame looks like. This is all of the elements you need to understand. So unfortunately, there's quite a lot of new terminologies here that you need to really digest. So as I said, what a portal frame structure is one that has got a vertical column, which is a portal column. It's got a rafter, which can be referred to as a portal beam. So it's got a column, a rafter, and a column again. Can we see that on the drawings? So usually what happens is you have, say, assuming this is a portal frame structure, you'll have the portal frames placed at regular intervals. So they can be at 10 meters, or they can be at 12 meters, or they can be at 6 meters, depending on the design. Okay, so you have one portal frame here, and next portal frame here, and then the next one, on and on. Is that correct? So what happens is, because this is the moment connection, so that connection there we have the portal and the rafter. That connection is referred to as what? What is it called? The knee. Remember I said that last week? That's the knee connection. So you remember your knee. It's the same. Okay, so that's the knee connection there. Okay? So what will happen is, usually what happens is you have a lot of moment, because when you have a portal frame like this is the very, very rigid. If you push it like this, it's very rigid in this direction. Is that correct? No? Can we see that? I don't want to draw because this is too early. So because this is a vertical and it's a moment connection here, so what I'm saying is, if I have the model here, so it's easy to explain. I've got a column. Oh my God, I've broken it. Shit. Damn. So what happens is I've got a column, I've got a portal rafter, a portal beam. So this is a column, a rafter, and another column. So this is a mirror image. So this is, if I push it in this direction, it's very rigid. Is that correct? Because it's taking moments at this connection here. Can we see that? But if I push it this way, it can easily just fall over if you push it this way. So this is the weaker direction, whereas in this direction, it's very, very rigid. So all the loads or moments applied on the portal frame is then taken mostly by the portal action of the column and beam. Does that make sense? So that is why we have a very rigid connection here. And that is why what you can see, I'll pass this around shortly. What you can see is you've got between one portal column or one portal frame and another portal frame, you've got it braced in that bay because it's a weaker direction. So it can easily be pushed over this way. To prevent that from happening, that's why we have a brace in that other direction. Does that make sense? So now let's quickly go through some of the elements. There's quite a few elements here. As I said, that's a column. That's what a column is called. That is called a rafter. Why is it? It's a rafter there. That's one. Or it's called a portal beam as well. It's the same thing. It's almost horizontal. So sometimes in some books, it's referred to as a beam. So as I said, because this is the rigid plane, when you push it this way, it's more rigid in that direction. What happens most of the time is the moment at this knee is very, very high. You can imagine as I've explained. So for that reason, the beam or rafter itself is not sufficient to take that moment. So what happens is, for you to be able to, the section to take that moment, we then add what we call a hunch. So that's what the hunch is. So that is meant to provide a deeper section at the knee so that it can resist the moments imposed on the section or on the portal frame. Does that make sense? So that's what the hunch is, and that connection there is called the knee when you have the column attached to it. Can we see that? So usually what will happen is that hunch is usually a cut out section of the rafter. So if the rafter is, say, 360 UB, that will be cut out as well from a 360 UB section. Does that make sense? Okay? So that's what you've got there.
But
so
the drawings, it's the knee itself that's called hunch.
What?
Not the...
What?
You see what's marked as hunch?
Yes, this is the hunch.
Oh, okay.
The entire connection there is the knee. It's a knee connection, it's called.
Okay, I thought you were talking about the inside.
That's the hunch. That member there is the hunch, which is a cut out. So as I said, this depth you have here will be the same depth here as well. Because this hunch is a cut out of the same section as well. But because we don't need that bigger section as we go away from the knee, that's why it's usually tapered and cut out and goes to zero.
Can you explain one more time what it does,
The hunch?
The hunch, yeah.
So as I said, when you have wind or load applied, usually it's wind load. It's a critical design load for these type of structures. When you have them blowing this way, which means it's blowing against this way, you have a lot of load transfer from the column to the rafter. Now, that moment that is generated from wind is very high. And just having the typical rafter section is not big enough to resist that moment. So to make sure that we have adequate section to satisfy strength and serviceability, we then provide a deeper section at the knee. So that is why we have the hunch added to the rafter. So then you have a deeper section which can take the moment. So tomorrow we'll look at the moment diagrams and you will see what I'm talking about. Okay? Does that make sense, guys? I'll pass those around shortly. So as I said, between one column and the next column, or between one portal frame and the next portal frame, it's usually connected by what we refer to as struts. So you can see the strut, okay? So the strut that is down at the eaves level or the end strut, which is next to the knee connection, is referred to as an eaves strut. Can you see that? Yes? No? And then you have series of other struts usually. So you'll have an eaves strut, you'll have an intermediate or internal strut, which is different usually from the eaves strut. So usually, because of the same moment that is quite higher at this particular end of the portal structure, you will usually see that the eaves strut is quite of a bigger section as opposed to the internal strut or intermediate strut. Does that make sense? Is that clear so far? How the portal frames comes together. We've got the wall bracing, which connects the two because of its weaker in this direction. You can push it and it will fall over. And then to prevent or connect this structure of the individual portal frames and make them all work as one, we then have series of struts. So those series of struts are different, and they've all got different names. The one at the end, which is next to the knee, is usually called the eaves strut, because that is next to the eaves. That's why it's called the eaves strut. And the other struts, like that one, so you'll have series of these, will be referred to as an intermediate strut or an internal strut. It's the same thing. Does that make sense? Now, it's the same thing as well, the same concept when you look at your assignment 1, you'll notice that the moment at the end span, so in your assignment 1, you've got what? You deal with an end span, you have internal span, and every other span. Is that correct? Same concept here. At the end span, you'll have higher moment because the factor is smaller. So for your moment factor, it was what? FDL square over 11, was it? For the end span. And intermediate span was over 16. So you have much more higher moments at the end as opposed to the internal span. Same concept here. So assuming, looking at that on plan, that's a roof level. You've got a higher moment at the end, and the internal moment away from the support will be much more smaller. Hence, you can have smaller section in those areas. Is that making sense, guys?
Is the rafter also called portal beam?
Yes, okay. The rafter and portal. So in some textbooks, I think most of the American textbooks, they call it portal beam, but it's the same thing. Because it's a beam and column structure, essentially. Okay, so that's why you can see here from the picture, you've got a smaller strut here and a bigger eave strut here, for the reason I've explained, because of the moment along the base. Is that okay? Make sense? And then if you look on plan, you will have what we refer to as the roof bracing. So that's cross member, this one, and that one on plan is the roof bracing, which I explained last week. So usually the roof bracing is usually most often at the ends, and sometimes you have them as well in the middle. But always you'll have roof bracing or wind bracing always at the end, and I will explain why that is the case later when I talk about the wind part. Now, in addition to the portal frame, you've got different other elements. You've got the wall elements. So next to the column, you'll have the wall element. And then that wall element, the wall cladding, will be picked up by what we refer to as the guts. So the guts, which is that element there, is what is being added to the column. And then behind the guts, you have the wall cladding. So that's how every bonings, for example, is constructed. And then, of course, at the roof level, you've got the purlins, which connect one portal frame to the next. And on top of the roof beam or the rafter, you've got what we call the cleats. So that's a purlin cleats, which picks up all the purlins that goes in this direction. Is that too much? It's very simple. Just spend some time and look at it. Okay, so if you look at the top as well on the outside, so behind the cladding, of course, or as part of the wall cladding, you'll have a roof gutter at the end, just as in a typical domestic structure as well. You'll have a roof gutter. So behind that roof gutter, what you'll have is, you'll have what we call the fascia purlin. So the fascia purlin is at the roof gutter level, which is usually the end purlin of all the roof purlins. So that's the last purlin at the edge before all the other purlins. So that's called the fascia. So the fascia is what you have like a fascia board in a typical domestic house, if you remember. So it's the same thing. Okay? So similarly as well as with the purlin cleats, you will have cleats as well attached to the back of this column, which picks up all the guts. And I will show you more detail as we go along. So, as I explained last week, when you have a column, okay, you've got a steel column usually, what happens is you've got higher moment, as I said, at that connection. That is why we usually have a moment connection from one member to another, and that is the reason why we have the stiffeners. If you remember, I explained that last week. Remember that? So that's the stiffener there. So to prevent local buckling when the load is transferred, so if you look at this, can you come and help me, please? If you hold this like that, if you just hold this like that, yes, hold it like Yes, exactly. I want the top to be level. Oh. Yes. So if you hold it like that, what happens is, now you can see. What happens is when the load is being pushed and then you have moment transfer from one member to another, what happens is you will have this will tend to do this or it do this. Is that correct? So the entire portal frame will tend to go this way or that way. So what happens is, can you hold it back again, the top equal? So what happens mostly, you likely, because the load is transferred from one member to another, from the column to the beam or beam to column, you will tend to have a damage of this column flange. Is that correct? At that point where it connects. So for that reason, that's why we have those plates, which are called Doppler plates. Do you remember that? I explained that last week. Oh, sorry guys, you're not seeing there. Okay? So to prevent that local buckling of the flange, you've got those Doppler plates which are placed next to the end plates. So if you look, thank you. So if you look at this, that is usually what we call the end plates there, as I explained last week, which you are not seeing there in this case. So that's the end plate. Okay? So that's the end plate, which is the end. Okay? That one I've broken that one just then. So that's what the end plate is. And then you can see from that, I'll pass that now around, you will see that what has happened is, to ensure it is a moment connection, what has happened, we've extended the end plate beyond the flanges so we can get a moment connection. So it's bolted at the top and the bottom beyond the flanges. Can we see that? I explained all of this last week, why we have moment connection. So we are lucky. These were made by Jen. She made them for us, which was quite a lot of work. I'll pass that and you'll see that around. Is that okay? So you should understand that diagram. That's why I've spent about 20 minutes just explaining that page, because it's very, very important for you to understand what goes on there. Any question on that? Do you have any question before I go forward?
Are girds taking any structural load?
The guards? Yeah. The guard is what is used to support the wall cladding. So it's like...
So no structural function?
It does provide some function, which I will explain later. Okay, so it prevents local buckling of the column flange as well. Any other question on that? Yes, no? Okay, we all happy? Okay, this is the heart of the assignment, so you need to understand all the terminologies here. So now, where you have the two columns, the two rafters meet, I will take that again shortly, please. Where you have the two rafters, where you have the two rafters meet at the top point there. Can you see that? So usually we'll have the rafters meet at the top point, at the highest point of the portal frame. What is that called? The apex. At least you remember that bit. Thank you. Okay, so that is called, I will not polish that one because it's broken. So that is what is called the apex, which is what you see there. So at that point as well, because of the change in geometry, from one member to another that is connected here, you will have a moment transfer between the two there. And that is why that connection usually as well is a moment connection at the top. And as you can see, it goes, you will see that in the one going around. The end plate goes beyond the flanges so that we can bolt them beyond the flanges to form a moment connection. Okay? Now, let's move quickly like a jet. Okay? Any question on that? That is very important, guys, for you to understand what goes on that page. So that's exactly what I've just explained. You've got a column, a portal frame, got a column, a rafter, and a column. That's what is called the knee. You've got the end plate, which I've just explained, and you'll also have a moment connection at the apex there as well, at the top point. So most of the time in the exams, what will happen is for you to tell us why things are done the way they are done. Okay? Sometimes what happens is when the portal frame is so big, you will have another intermediate connection here. So like the one we're going to, it's got, I think, 3 internal columns, and the length of it is about over 100 meters long. So it's mighty, it's big. And it's over 100 meters wide, and over 300 meters long. Luckily, he printed the drawings for me the other day. I hope you didn't take a copy of those drawings, because you'll be in trouble. Okay? So what happens is when this is quite big, usually you will then have series of internal columns. So those internal columns, because they are usually in the middle, they're small, moments transfer between the column and the rafter, they usually tend to be made out of a smaller section. Is that making sense? So what I'm saying is not here. What usually when you have a very big span, say from one point to another is 100 meters, you can't have that span 100 meters by itself. So what we do is we break the span. You will have an internal column here and an internal column there. So most of the time in that case, those columns are made out of SHS, which is this I'm having here. This is an internal column. Okay? So most cases, what will happen is the rafter will basically just sit. This is a different connection. The rafter will just be supported like this if the span is too long. Just pin supported. No moments transfer in that particular case. Now, sometimes, as exactly with what we're going to see on site, you don't have a hunch like this. The hunch usually becomes a much more deeper and bigger member over a particular span. So when we go to site, you will see that the hunch we will see there is different from what we are seeing here. This is the traditional one. So sometimes what happens is when the moment is really, really high, they will have all of that section, maybe 2 of it, being uniform, and then it's reduced in the middle. Does that make sense? So that is what you're going to see. You don't see this hunch when we go to site. It's a different hunch they have used in this site we're going to next Monday. They've got a much more deeper section which is being used, and then it terminates somewhere, and then it's continued with a smaller section to the next connection. So in that case, they don't have one that has been cut out. I can pass this around as well if you want to see. That's the SHS, what it looks like. So a rigid connection can be welded or can be bolted. When it's bolted, the end plate has to go beyond the flanges so that you can provide bolts and form a moment connection. Sometimes it's fully welded. And in this case as well, what we're going to see on site is different. So that's why you have to come to the site visit. Okay? Okay? Now, as you can see here, these structures are very, very big. They're very difficult to transport because one thing is transporting them to site. So sometimes what happens is the engineer will have to come up with some very, very clever sort of design where you tend to provide a connection, which will be a pin connection, where you have very, very little moments transfer between at that point. So if you understand what a bending moment diagram usually does, you'll see that, for example, in this case, what will happen is the moment is huge here, and as it goes towards the center, it reduces. So what the engineer has done in this case, as here, what you can do in most cases, you will have what we refer to as a bolted splice provided, where the moment is smaller or almost zero. So what that means is it enables you to make these sections smaller, transport to site, and you bolt them on site. So usually, a bolted splice is just a connection where you just bolt two members together. That's what the bolted splice is. And it will have what we refer to as a splice connection. Okay, so that's why, as it says there, the transportation limit is an issue in most cases, like particularly in portal frame structures. So they are usually made in various lengths so that when they transport to site, they can easily be bolted on site. And the connection that is formed usually referred to as a bolted splice connection. So now, as with every structures, you've got dead loads and live loads. So in this case, we've got dead loads, which we consider, which is all what we have as part of the structure. So that includes the roof sheets, weight of purlins, and all of that. And usually with these structures, they have to be insulated because most of the time it's a lightweight roofing they've got. So they have to be insulated so that it's a warehouse, people are working in there, so it becomes very comfortable when it gets hot. And with our weather in Melbourne, for example, or in Australia, you know how crazy it gets in the summer. So that's why you have to take account of those superimposed load. Usually in these structures as well, it's an industrial structure. According to our own standards in Australia, we have to provide fire safety measures in place when we build them. So usually you will have a lot of elements added to the roof internally to ensure that the structure itself functions well. So one of the services that will be, which I don't think we'll see at this stage because it's not at that stage yet, will be the fire sprinkler services, which is what you should have here. Is there any fire sprinklers here? I can't see any. So you should have them. Is that it? Is that an alarm? That's an alarm. There is no fire sprinkler here. That's weird. You should have a fire sprinkler. Okay? But if we see that on site, that will be a bonus. And as well... Sorry? Well, you all know what a fire sprinkler is. It should be somewhere. It should definitely have fire sprinkler, despite it's an old building. Now, we also have live loads as well. So live loads are actually taken into account, as we know, for the roof structure particularly, because sometimes you will have to go onto the roof structure to do maintenance. So we have to account for this. And with, you know, these days we're talking about green technology and sustainability of our buildings. We tend to have additional panels as well. So most of the time, solar panels are much more lighter than a live load for a roof. That's why most of the time you can add solar panels to a roof. So for live load, usually it says that we should take into account a 1.1 kilonewton, which is 110 kilograms of load over every square meter. Okay? And that live load, as you can see, it's considered for a worker that goes up sometimes if you are going to use equipment on the roof. And in areas that it snows, live load for snow load is considered as well as part of the design. Okay? In Australia, we don't consider snow loads. Now, for industrial structures, because of their very, very gigantic structures, they are huge, and most of the time they are built like a standalone building up, you know, or around where you don't have many other buildings around them. For that reason, the wind load often is the critical load on these type of buildings. Anyone here have not seen a Bunnings before? Have you seen a Bunnings? You seen a Bunnings? What the Bunnings is? No? Oh my God. You should know what a Bunnings is. So a warehouse, you know, it's a supply chain which sells hardwares. Okay? Now, Bunnings sometimes in the city because of, you know, changes in demographic these days. But sometimes, like the JBI Files, like the Coles, like the Woolies, they don't stock everything on site. So what they do usually, they will have what they call a distribution center. So the distribution center is where everything is stored. That is why when you go to a store, you want to buy a TV, they'll tell you to bring it in 2 days. They're not bringing it from China or from Japan somewhere. It's somewhere in the West or somewhere in the Southeast where it's been stored. Does that make sense? So even Coles and Woolies, all of these stores have what we call distribution centers. So usually when they are built in an open area where the wind load is quite high. So it doesn't have, like in the city where you have a lot of shielding or the buildings around it, if that makes sense. So when that happens, because of that reason, the wind load are usually the governing design loads for industrial buildings. So most of the time, of course, we have to design them for 50 years return period, so they have to last at least for 50 years. In Australia, in our design guide, as I have explained, the reason why they are built, you know, out in the West, because they have to distribute goods to their shops. We have to consider different, what they call our terrain category. So the terrain category basically just explains how exposed the structure is to wind, basically. Does that make sense? So based on the terrain category, okay, that basically controls what wind load we can use to impose on our structure. So just as an example, if you're building somewhere in Richmond or in the city, as opposed to building a structure in Thanet or Point Cook, which one you think will have exposed to more wind? Why? Because of... Exactly. It's windy because it's got what we call scattered structures. It's very open area. Whereas in the city, you've got a lot of other buildings, which is going to provide shielding to your building. So it protects your building from the wind effects. So it means structures that are out, like in the airport areas, which is open, will be exposed to more wind. So which means they are much more prone or critical for wind design. So in that case, you'll see that if you are building somewhere like in most domestic areas, which is compact and have a lot of structures, usually we consider a category 3, you see the wind pressure is very, very small. Whereas if you build in open areas, as it goes up, it increases. So the most critical one is category 1, where there is virtually no shielding to your structure. And you can see the wind pressure is, what, 2.5 times almost the category 3 wind pressure. So it means if I'm building in the city or in Richmond or Brunswick or North Melbourne, consider category 3, I can use 1 kPa of wind load. If I'm building in Thanet area, open areas, I have to do 2.5 times that. So if I apply 1 kPa of load in a structure in North Melbourne, in Thanet or that end, I have to apply 2.5 kPa of load. So it means it becomes more expensive as well, if you get what that's the implication. Okay? So that's the load terrain category. So I'll show you some photos on that. So in Australia, we've also got different regions. So we are lucky here in Melbourne. It gets windy, but it doesn't get windy because based on the wind classification in the standard, you've got what we refer to as region A, region B, up to region D. So region A are areas like where we are in Melbourne here. Melbourne, part of Adelaide, Sydney is all region A. And region B, as you can see, goes out into the coastal area, so that's Queensland there. And region C, where it is very, very, very much dangerous going forward, out in the coast, so where you can have very, very high winds. And in region D is that section there in Western Australia. So what you can see, if you consider a particular wind speed, okay, for region A, you will see for an annual probability return period of 100 years, V100. Region A is only 41 meters per second speed you can consider. Whereas for region D, it's almost double, of 82. Can we see the difference? So it just explains to you the impact when you're building along the coastline as opposed to building somewhere inland. Does that make sense, guys? Okay? So usually the engineers will have to use this to sort of classify where you build, and based on that, they used a certain terrain category, and based on that, they develop what the wind speed or wind pressure to be applied for your structure. Okay? So looking at it in depth more, so that's the same table, just showing you a lot more detail, where you have region A, region B, region C, and region D, as I've explained. So when we are here, we have 100 kilometers an hour of wind, and we complain. If you go to somewhere in Queensland, Northern Territory, you have 2 to 3 times that speed. So it tells you that when you build in Queensland, Northern Territory, the way they build there is completely different to how we build here, because they have got a lot more wind. They've got cyclone in Queensland, for example, so they've got a different classification. So all of that tells you that, you know, if you're building there, it's more expensive because you're going to have more robust structure, more expensive design, and then it becomes more costly. Okay? So if you have a land somewhere in Queensland, don't come to Melbourne and do the design and take it to Queensland and build. It's not going to work. It's going to fall down the next day. Okay? So now, look at the terrain categories here for you to see it clearly. So in the Australian standard, we've got 4 terrain categories. We've got category 1 to category 4. Okay, so category 4 is like where you have all the tall buildings, very, very compact. Less wind pressure on the buildings, more shielding, and it's more safer. Whereas in terrain category 1 is where you have nothing shielding your structure, as I've just explained. So usually, as you can see, it gives you example there. So like category 1, open, like a lake or the river or the ocean. All of that usually comes in that category 1. So 1, 1.5, or you can have 2, which has got scattered obstruction. So scattered obstruction means you've got one structure here, the next one is there, the next one is here, the next one is there. They are not quite close to each other to shield each other. Okay? And then, as I said, category 3 is what you use mostly where you have medium density housing, like in Richmond. When you do domestic structures, mostly you use category 3, for example. So that's an example there, showing you the different categories. So you can see, if you go to Antarctica, you want to build a structure there, it has to be category 1, because it's very, very open, dangerous, a lot of wind. If you want to build a structure offshore in the sea, okay, it has to be a category 1 because it's open and it's a lot of wind pressure. Whereas, as I said just then, a category 3 is used for density areas, and a category 4 will be like in the CBD and in most cities around, or in most dense city areas around Australia. Okay? So that's showing you as well what we refer to as height multipliers. So what that means basically is factors that you can use. So as you can see, when the building height is lower, the factor there is smaller. So as the building height goes up, the factor becomes much more higher. And that is the reason why when you have a design being done by an engineer, you're on site as a construction manager, as a project manager, you make sure what is on the drawing is implemented. Because for some reason, if you didn't do according to that has been designed, you might be in trouble. I was doing some work the other day, as an example, I'll give that to you, that this happened in 2014, just as an example. The owner contracted the builder to build two townhouses, 2 of them, to each other in Blackburn. What happened was the builder, because he was trying to get some more profit, excluded the spoon drain that was designed as part of the slab. Okay? The contract value was about $970,000. I was just reading this yesterday. What happened? 6 months later, water gets under the slab. The water was not taken away from the slab, and then the slab heaved, pushed up. And then the builder went into trouble because of that. So just a small, tiny elimination of the spoon drain tells you that affected the performance of the building. So these are the implications. And you as a builder, you have a reputation to protect in the industry. So you want to make sure that you do what is being done. Now, when you have wind load, when wind blows, I don't know whether you did this in materials and structures, you're supposed to have done this, you have what we call the wind direction. So assuming wind blows this way, like it says there, so when wind blows this way, you'll have a positive pressure, is it, because it's blowing this way. But because wind, if you look at the wind action moves like in a circular form. Doesn't move like linearly. So it moves as it goes over scattered surfaces, it sort of rolls. So what happens usually, if that happens, wind blowing this way, it rolls. When it comes to this side, it goes under and it sucks in again. So that action is referred to as suction. Does that make sense? Okay, so that's the suction action. So usually when wind blows even over your car, and that is the basics on which the design, cars that move very fast is based on their action when they drive against the wind. When it blows, it provides or produces positive pressure, and that pressure goes around the structure and above the structure, and it calls in again and forms what we call a suction. So that suction is a negative wind pressure, and the positive wind pressure which impose or gets imposed onto the structure is a positive sort of structure. So when we do the design, we have to account for all of these actions on our structures. Okay? I would not bore you with the coefficient just to explain the action. So when you look at this is what I'm saying. So when wind blows, it goes and then it calls in and sucks in again at the other end. And that is why if you're at home on a windy day, if you go to the other end of the house where wind is not blowing, you will still feel the wind coming to you because of that suction action. Okay? So why that is important? Because that actually affects how our portal frame structures behave internally. Because what happens is when you have wind, so if you know what a bonin structure is, a bonin has got very large doors, maybe the doors about 15, 20 meters wide. Okay? What happens is when those doors are open, a lot of wind comes in. So that wind can actually push your walls internally over as well, because there's a lot of wind. And forget about the walls, which probably might be properly tied down. What is more critical is the roof structure. That wind can push the roof upwards and throw it away. That is why sometimes you find the roof of the house down the road when you have heavy wind, because it's not properly built. And as well, it also affects our rafters and our columns, which is the question we were asking before about the guards. I will explain a lot more on that later. Okay? So as I said, when you have a large opening here, you've got positive pressure, so that pressure gushes in. That will push against all. So assuming this was open, that door is open, wind comes in, it will push this wall and push all the walls around, tend to push it out. So that's what you're seeing here, pushes it outwards. At the same time as well, you've got suction, which is on the other side, on the outside as well. Okay? So what happens then is when you have internal pressure, so I have my rafter, I have internal pressure, it pushes up against the roof, and as well it pushes up against the bottom flange of my rafters. Is that correct? Can you imagine that? So it pushes, wind comes in, as I said, assuming that door is not there, wind comes in, wind blowing, so bonus doesn't close because the wind is heavy. Wind outside is 100 kilometers an hour, comes in, a very large opening, and it pushes all the walls around. And at the same time, I've got all of these portal frames. I've got all my rafters sitting every other 30 meters. Usually they are set. So that wind pushes up against this, and most likely what will happen, it's likely to push that and produce bending on that flange, and it's likely to fail. So to prevent that, we have to make sure we do something to ensure that action or that bending does not occur. Similarly as well, when you have the column standing next, assuming that's the column standing vertically, wind blowing, wind comes in and pushes against the wall, all the walls, that column is likely to, the flange is likely to fail as well because of that pressure. Can we see that? Okay? So when we do our design then, we have to make sure that all of that is considered and taken care of. So when you're building, you will see that we provide certain elements that sort of prevent that from happening. So what you're seeing here is internal pressure pushes up, so that's the action. It pushes up against the rafters or the portal beams. It also pushes against the columns, which I've just explained. And that will also generate bending on our frame, our portal frame structure. Okay? Whereas if you have a smaller opening, the pressure that, because of it's smaller, the wind that comes in will be smaller, and the pressure that pushes up against all the internal elements will be smaller. That's why here we've got a much more bigger coefficient for a large opening, and we've got a smaller coefficient for a smaller opening. Okay? Now, what happens is in most bonins, if you go into a bonins, you always hear the fan spinning, something like that. It makes that sort of noise. Okay? So what that actually is what we refer to as a ventilator. So what that is doing basically, when wind gushes in, it's actually sucking it out again. So that's the mechanism that is being used to minimize the amount of wind pressure you have internally in these structures. So they are referred to as the roof ventilators, which are used to reduce the internal pressure. They are very expensive, but when you look at Bunnings, it's a supply chain, it makes a lot of money, they can afford that. Okay? Does that make sense, guys? Okay? So looking at some of the loads, again, these are just some design loads for you. So in Melbourne usually is one of the milder areas. So that's what I'm saying. If we complain about windier, imagine people in Queensland what they are saying, or in Northern Territory. They are actually dying with the wind. So you can see here our wind velocity is quite small. 39 usually is the minimum considered in our design. Sydney is more windy, and you can see Brisbane is even worse. And as you go into the cyclonic area, like in Northern Territory, look at the wind speed there. It's very, very, very high. More than 50% of what we observe in Melbourne here. Okay? So when we do our design, basically, we have to ensure that that structure, when it's cladded, imagine when you have a structure like this, say assuming this is a portal frame structure, it's cladded, and then it's windy. So all the cladding attracts wind. Is that correct? Yes? No? So you have your house built in the middle of nowhere, scattered obstruction, no shielding. What happens then when it's windy is you've got cladding. So the cladding is the material that's been used to cover the building, part of the envelope. That's what the cladding is. You have all of that cladding. You have the roof cladding, and the building is locked at night, and then it's windy. So you'll have a lot of wind attracted to that building. Is that correct? Because of the surface is solid, in other words. So it's like just your house at home. Your house at home, you've got brick cladding, if it's a brick veneer house, and then when it's windy, it attracts wind, when wind blows, normally. Even when you walk in the wind, you get attracted to the wind pushes over. Same thing like the house. So normally what will happen is, this surface area, okay, which you should have done in material structure, as I said, when you have wind, that wind load is attracted to a larger surface as opposed to a smaller surface. Is that correct mathematically? Yes? No? You guys can't understand that. Is that too hard? No, you don't have a break yet. We have another 10 minutes, then you have a break. Let me put it this way. If you have a van, you're moving home, you rented a van from Budget or from one of the cars people. You park that vehicle in the middle of Point Cook. And then I have a car, which is smaller, a small Mini Cooper. And I park it next to the van. And then the wind is blowing against them. Which one are you going to fall over or push over easily? The van or the car? The van. You agree with the van? Yes. Why?
Because the area is larger.
That's the same concept I'm explaining here. It's the same concept. Okay? So, yes, that's why I made it simpler that way. So, because of the van has got a bigger area, it will attract more wind. Is that correct? So, in a bonding structure, one side is shorter and the other side is longer. Or in a warehouse structure, that's how they're built. It's not square or rectangle. It's a rectangle, but very, very elongated. Usually a ratio of about 1:3. 1:3. So the one we are going to, for example, is 1:3. One side is 110, the other side is 300 meters long, 320 meters long or so. So it means this area here will attract a lot of wind. So now what I'm trying to explain is to tell you why we have the moment or rigid frame in this direction. Because you'll have more wind along the longer direction, and it will tend to push this or lift it off and push it over this way easily, as opposed to if you want to push it this way. Do you agree? You're still counting your fingers. Does that make sense, guys? Okay, so usually the wind is more critical along that longer direction. And that is the reason why our portal frames goes up this way. So what that means is, because this one is likely to be pushed over this way, that is why we provide the rigid connections this way. Does that make sense? So that is the concept of having a layout as it is done, usually. Okay? So normally you'll have the zero wind direction will be the most critical direction, and every orthogonal direction will be the wind at 90 degrees. Okay? This is all being done by the engineer in the office, but you building it, you need to understand why it's been done that way. So this might be an exam question to say why the building layout is being done, or why we have the rigid portal frame in that particular direction, which is what I've just explained. Okay? All right, we'll have a 5-minute break there. Any questions before you go? No? We're all happy? Okay, have a 5-minute break and we continue. Where are the models? Please don't take them home. Where are they? Who's got this one? Have you got it at the back there, guys? Where has it gone? Do you have it there? Why is the other one? Please don't take it home. It's expensive. That's right. A lot of time. All right, guys, come back. We've got a lot of ground to cover.
Technically, it's not the cladding that attracts the wind, it's the surface.
Yeah, the surface.
So increased area.
Yes,
actually attracts
more wind.
Not the cladding itself.
Not the what?
Not the cladding itself. It's the increased area. It's the
Yeah,
increased
so
covered
it's
area.
the cladding, the area of the cladding. All right, guys, let's make a start again. So now we're going to go through quickly. Sit down, quick. We've got a lot of things to cover. I've got about another 20 slides or so. Or 16 slides. All right. So now we've got the roof and wall sheeting. So that's the roof and wall cladding. You've got different manufacturers. They all do the same jobs, and most of them have got the same properties. So usually what will happen, the manufacturer will provide you with an installation manual or a data sheet which tells you how it should be installed, basically. So one of the popular ones, for those of you working will know, is what we call the Lysat clip lock. They make a lot of cladding elements, so they do roof elements, they do wall elements as well. And they have got different sort of different cladding and roofing elements that you use for cyclonic and non-cyclonic areas. So in Melbourne, Sydney, the inner city, it's a non-cyclonic area. And when you go out into Queensland, Northern Territory, Western Australia, that's a cyclonic sort of area. Okay? So usually they provide roof spans, tables as well. So span tables, which the engineer use to do the design. So a typical clip lock Lysat one is normally has got 2 trays, and it's usually 203 between the ridges. So that's the ridge, and then it's got what we call an underlapping rib there. Okay? So when you have this roof sheet goes over a series of rafter, then it becomes what we look at like a continuous beam. Yes? No? I'll show you here. So if you look at this, is this like this in your lecture notes? It's cut? Yes? Oh, okay, it's right there. So what you have here, as I'm saying, please look at this. So you've got, this is a portal frame. You've got a purlins which goes over. Is that correct? Huh? So what you see here, for example, you've got purlin. So which means that roofing sheet is the black line. It becomes a continuous sort of member over the series of purlins because the purlins act as support. So what happens is you then have what we call an end span, and an internal span as well. So similar to your assignment one, same thing, same concept. The reason why that is important because that tells you at the end span you've got higher moment, so which means you have to do something when you're doing the design, if I'm the designer. So what happens generally is where you have the purlins at the end span, because of we've got higher moments there, okay? So O, there is the overhang, so it overhangs there. And in that bay, you will have a much more higher moment towards the knee. What that means is normally, what you'll find when you go to site, you then have the purlins more closer than they are spaced in the internal span. Does that make sense? So usually, the span, the end span, which is closer to the knee, which is that one there, probably the first two spans will be critical. So the end span and the internal span will be critical. You'll have much more higher moment. What will happen then, you will have that purlin, and that purlin made out of a different section as opposed to all the other purlins. So if the end bay or end span there has got a much more higher moment, what will happen? The engineer will provide. What do you think will change? The depth of the purlin or the wall thickness of the purlin? The depth. Well, if the depth changes, how do you have the roof sheeting goes over? So that's the purlin there. I will show you what this does. So that purlin, because it has to form, so that's the slope, that's my slope. Okay. So my portal frame goes this way, and this forms the slope. Okay, goes across. The slope goes this way, sorry, and then the purlin goes this way, as it is on the board. So what will happen, as I said, at the end span there, you will have higher moment to resist. So what happens is, the height has to be the same. So what will happen is, the thickness of those purlins will be much more thicker than all the other purlins internally, because you don't need the thicker one there. Okay? So this is a typical typical table provided by Cliplock, which is normally used to design the roof and wall sheeting. So as you can see here, if you have a single span, so a single span means you have two supports. You just have the support 1, 2 at the ends, and you've got the roofing sheet goes across. Or you can have multiple spans, which has got end span, internal span mixed together. So as you can see here, if I've got a span is, say, for a single span, the span from one support to another is 1.5. It tells me that for serviceability, the wind capacity the roof sheeting can take is 2.07 kPa. So what that means, what that is important as part of my design and construction, if I'm doing a D&C, which is what happens mostly in this type of projects, okay, I will then calculate my internal suction, my internal pressure, and based on that, I size up what I need to specify. Does that make sense? So that's very, very important. So you can see that when you have an internal span, okay, because it's internal here, for the same 1.5, if you have a continuous one, you can see it takes a lot more load of 2.66 because it's continuous as opposed to a single span. Okay, so you've got different configuration or different corrugation, you call them. So you've got different Cliplock. You can see you've got Cliplock high strength and the Cliplock classic. These ones, as I said, these tables mostly are used in the office, but most of the time, if you are a construction manager working for Quanstruct, for example, or Frasers, they have to do design and construct. So you need to understand how to interpret these tables. That's why we are going through some of these elements. As part of the tables, as you can see, it tells you what the BMT is. What is BMT? Huh? It's not bending moment. What is BMT? Guys? Yes, base metal thickness. That can give you 1 mark in the exams, just so you know. Okay, so it tells you the mass. So that's the base metal thickness means the thickness of that. That's what BMT is. Okay, tells you what the cover width is, what width is. It just covers the rib, depth, and so on. So these are just properties of the different sort of different configuration. So please try to understand what single span is, end span, multiple span, what is internal span, and the end span. Because the reason being, in the data that will be provided to you, which I have put together, I'll get that to you, as I said, by tomorrow. You've got like the strut for the end span, you've got the strut for the internal span. All of them is different. So you need to actually understand what they are. Otherwise, it's very difficult for you to sort of understand. That's why I actually have to clarify those SS and ES on the drawings. And normally as well, with the roof and wall sheeting, as I said, the manufacturer specifies how it should be used. So when you're on site, you see the tradies doing the roof are doing something different, make sure they comply with what the spec says. Because usually the manufacturer has to specify, for example, how you can lap the roof and wall sheeting. So Clip Lock has got the recommended overlapping cogs. If you have different configuration, say if you have a simple, this one is a custom blue one there. If you have a configuration like that, it tells you that you need to at least have 2 cogs overlapped, and it tells you exactly where you have to put your nail or screw at the roof level. Because sometimes what will happen, the tradies will put the screw in the middle there, which is wrong. So you need to understand what is right and from what is wrong, and how the cogs should work, which is what that is saying, and lapping should work. So Clip Lock, I actually have the Clip Lock in the office, but it was too much for me to bring, so I left it in the office. It's got a very simple mechanism. I might bring it next week when we're doing composite construction. It uses the same mechanism, where it just sort of, one of them just goes into each other and clips like that. That's how it works. So that's what you're seeing here. So it's got an overlapping rib, which easily just locked into the next one. And usually some of them have some a concealed clip. So what you can see here is you've put that down, okay? And then you've clipped, or you've sort of tied that down to the purlins underneath. And then you put an overlapping sheet, so you don't see any of the screws. That's why you see some of these roofs, when you go to site, these industrial building, you don't see anything, as if it just sits up there, because it's got sort of an hidden mechanism, how it's been connected. Now, purlins and the guards. So the purlins, as you know, is what goes onto the roof. You can have a Z purlin, so that's a Z purlin, that's what it looks like, if you haven't seen one. Or you can have a C purlin, which looks like that. So C is a standard section, and Z looks like a Z. So you can use any of them for the roof purlins or for the guards. So the guards is what goes around and receive the cladding. So these ones here, so you've got my column, and then I've got these ones are the guards, which picks up the cladding at the back. Does that make sense? Okay? So they have got different capacities, different properties, and I will explain what we use. So these ones as well, when they are used, because I've got one portal frame here, and then I move on another 30 meters, I've got another portal frame. I move on another 30 meters, I've got another portal frame. So the portal frame structures are placed parallel to each other. What happens is these purlins span from one portal frame to the next portal frame, to the next portal frame. Is that correct? Can you see that? No? Let me go back to that structure here. So I've got my portal frame here. So assuming that wall there is a portal frame, I will have one portal frame. I will have the next one in the middle where the row is. I will have the next one here. I have the next one here. I have the next one at the wall. Is that right? And then I have the purlins going in the other direction across them. So that's what I'm trying to explain. Got my portal frame like this. That's how it sits, and my purlins goes this way. Is that correct? So the purlins goes perpendicular to the portal frame structure. So what happens basically is these purlins are acting like a beam because they expand from one to the other. Okay? So if you go back there, that's why you see they principally act as a beam because of how they are connected to the portal frames. So what they do basically as well is to ensure that the portal frames, remember when you have the portal frames, as I explained before, this way, portal frame this way, I've got my purlins this way, they sort of prevent the top of the portal frame from doing this, is it? If its wind is blowing this way direction. So it sort of acts as a top restraint of the rafter, in other words. Can you see that? That's what they do. Okay, so that's why it says that they perform a strut and tension tie in laterally restraining the rafters and columns. So similarly as well, when you have the column, so that's my column, I've got my portal frame, this, so the next one, that one goes back like this, okay? So it's also help the column flange or restrain the column flange from moving inwards this way. So the column doesn't do this. Is that correct? Can you see that? Column doesn't do that. So that is why, as it says there, it then provides stability or helps the column against buckling. Now, when you have a column like that, okay, you've got series of guts. What happens is when the wind blows this way against the cladding, because the cladding is huge, it attracts wind. The area is, surface area is huge. Wind is blown on it. That gut is sitting on the back there at different levels. So maybe you'll have them as designed, maybe 1,500 high, 1,500 apart, and this is 10 meters tall. Then what happens basically is that column flange is likely to buckle. But when you have, because the column is too tall, so when you have those guts, sitting at different levels, it then reduces the effective length of the column. Do you remember that word in materials and structures? Yeah? So that is how it helps the column or restrain the column against buckling. Okay? If that is too much, you might have to go see James and ask for a revision class. Okay? So another thing that as it says there, it acts as axial member, transfer wind load to the brace bay. So when you have, as I said, you have a series of columns, so let's pay attention, please. This is very important because this is part of an assignment question you have to answer. You have that end wall there, assuming that end wall is one portal frame, it goes up, you have the rafter and column. I've got another one in the middle here. Okay, I've got another one in the middle of the class here. I've got another one here, and I've got one at the end. So I've got 5 portal frames. Is that correct? Then I have my purlin sitting like this from one to the next, to the end. So what happens is, in most portal frame structures, the end base, so if I go back to the very first slides, here. So what happens is, the end base, so which means between the first portal frame and the second portal frame, this portal frame and the last portal frame at the roof level, it's braced. You have roof bracing, which is this XXX you're seeing. Is that correct? Sometimes they can be braced over 2 bays. So from one portal frame here to the next portal frame there, that's 1 bay. From one portal frame here to the next portal frame here is 1 bay. Sometimes the roof bracing can move from here to the next one there, and then comes in again. So it goes over 2 bays. Is that making sense? So when we go back here, my God, what's going on now? Now it can't move again. Where is the expert man? It's frozen. Maybe we need to stop the class. Okay, it's working again. Okay, so what happens is when you have the purlins, what I'm trying to explain is how the load transfer mechanism is done in a portal frame structure. So what happens is when you have the purlins, okay, sitting this way, assuming I have my 5 portal frames, wind blows from one side. I'll use my left hand. So wind blows from one side, which is the smaller side, against the end of the portal frame. It tends to push the portal frames over easily because that's a weaker direction, which I've explained before. Is that correct? So the purlins at the top, what it does is it restrains the top flange of the rafter, and it transfers the load applied at the end from one braced end all the way to the other braced end, because it goes along its strong axis, because it's very hard to bend this way. You cannot push. You cannot fail this in this way. Is that correct? So that is why we usually say that the load transfer mechanism in a portal frame from one brace bay to the other brace bay at the roof level is done through the purlins. Can we see that? Because you've got one portal frame here, one portal frame here, so I've got a column, a rafter, and a column. I've got that 5 times, and then I've got my rafter sitting at the top. So when wind blows in this direction, this is at the top, prevents all the rafters from moving or falling this way. So this is in addition to the struts you have. So because of that, you will notice when you go to sites that it's only the braced bay will have struts. Otherwise, the purlin is what provides restraints to the portal frame at the roof level. Does that make sense? Okay? So that's how the load transfer mechanism is done. So what I'm saying, I'll go back to there is a structure here, this one, here. So when wind blows this way, I've got a portal frame. So I've got bracing at this end, and I've got bracing at this end at the roof level. All the load when wind blows in this direction is transferred from one brace bay to the next brace bay at the other end with the action of the purlin, because it provides restraint at the top. And then at the same time, you've got a roofing sheet, which is over the purlins, and that provides a rigid diaphragm action at the top of the, at the roof level of the portal frame structure. Clear? No? Yes. Yes? That's good. At least somebody say yes. Okay? So that's how it works, basically. Okay? So usually, as I said, so that's line, says discuss. That's what I've just explained, how the roof bracing work and how load is transferred from one end to another using the portal frame. Yes? Oh, okay. So the C-sections, I think I explained this before, they are made out of cold form sections. They have a much more higher strength. So now in Australia, these are made up to about 550 MPa, so it's very, very strong. But I think I explained the element of being strong does not provide ductility, so that is a negative part. But usually, because the design is being done at serviceability level, it is most likely that they are not going to get into their reserve strength. So most of the time, you don't need the ductility aspect of the section. Okay? So usually, they come out in 1.6, 2, 2.5, and 3 millimeter BMT. So when you look at I can't see, I'm getting old. When you look at this, I will pass this around. Take a careful look. You will see it says Lysat, blah, blah, blah. I don't know what that is. But then it says C150-15. So C150-15 means it's 150 deep, and the wall thickness is 1.5. That's what that C150-15 means. It's somewhere I will explain shortly. So I'll pass that around for you to see. Okay? So now, what happens is when you have the purlins, as it says, on the roof structure, what will happen, as I've explained, the purlins, because my 5, I'm using my virtual 5 portal columns. When you have the portal frame and then you have the purlins, what happens is they span from one portal frame to another. So you can see it's got a very, very much bigger span between the portal frames, between the bays. So what happens is if you have wind blowing, okay, because it's between one portal frame to another, which might be maybe 10 or 12 meters, that's really wide. To make sure that this bottom flange, when you have wind blowing up, this one doesn't fail, we then have to prevent that bottom flange from failing by using what we refer to as a bridging. So when the portal frames, as I said, I've got my rafter this way, and then my purlins goes over. What happens is this span from one portal frame to the next portal frame. When you have wind blows upwards, that bottom flange of the purlin is likely to fail. Is that correct? So it's likely to fail in what we refer to as the outward direction. So when wind blows internally and pushes up the roof, it's an outward loading on the purlin. So it will fail the bottom flange of the purlin. And if that happens, it means you compromise the integrity of the roof structure, because this purlin span from one rafter to the next rafter and support the entire roof. So if any of these fail, the structure might be, fail. The roof structure might fail. So to prevent that, we then use what we call a bridging. Can you see that? That's a bridging. So the bridging basically is bolted to the face of the purlin. So that bridging is bolted here. So what that does basically, it reduces the effective length of the purlin from one bridging to the next bridging. So the effective length of the purlin is reduced. So in other words, because the portal frame might be about 12 meters, if I have two bridgings in the center, then that reduces to about 4 meters apart. Does that make sense? So what that does, it ensures as well that the purlin has got a much more higher capacity. So that's what a bridging looks like. It's this element. That's what you see in there. Can you see that? So what happens is this goes, I have to be careful. This is smaller. This goes like that to the purlin. So if I have my purlin 10 meters apart, I have two rows of bridging, maybe at equal distance, about 3.5 meters. What happens is this is at 3.5 meters, the next one is another 3.5 meters apart. Then it ensures that there is no sag in the middle of the purlin, which is 10 meters between the rafters. Does that make sense? It's very hard to see. That's why you have to come to the site visit. Okay? It's very difficult at times to explain. So that, oh my God. So that's what that is sort of explaining.
What's the connection in between?
It's bolted. It's just bolted. Yes, it's bolted.
What about in the middle?
There?
Yeah.
So that's a turnbuckle. You know, the turnbuckle is just used to tighten it if you have very, very long ones. So a turnbuckle, I can't imagine how to explain that. Unless you see it, you will know what a turnbuckle is. So that's a tightening mechanism, which when you rotate, it sort of tension it. Okay? So for those of you if you're working on site, you will know what that means. So hopefully when you go to site, we'll see that. So on the outward load, which is what I've explained, wind comes in, it blows upwards, that's an outward load. And the wind that blows from the outside in, pushing the roof downwards, is called the inward load. So that's outward, in, out, and inward is from the outside in. So as I said, to prevent the bottom flange of the section in compression over each span, it is necessary to provide bridging. So it means that that upward load doesn't push this and fail that bottom flange, which will be in compression.
So that connection is two separate pieces, and
Yes, that's usually you don't actually have all the time you have that, because the purlins now, that might be an old picture, because now what happens is the bridging is actually made to specified length. So it comes from one purlin to another. Most now that's what you'll have on site.
What if the span is too low?
Then you'll have a turnbuckle. Okay? Okay? So I think, now, there is a question here. Say, end spans are critical for polling design, which I've explained. So which means you will have a higher bending moment and higher local pressure around the perimeter of the structure. So what would you do? I think I already given you the answer with the pollings. What do you do with the pollings? So you have a polling design like that one, 150.15. At the end, as I said, you always make the polling with a thicker wall BMT because that is where it's critical. Okay? All right. Now, when you do our pollings as well, okay, you've got the columns. So I'll start with the roof first. You've got the roof. So assuming I've got the roof, I've got my apex at that point, assuming it's just a two rafter section. So that sits on the rafter like that. So to connect the polling to the rafter, you need to have a cleat plate. Is that correct? So that's what you see in there. So you need to have the cleat plate. Now when you join in either a Z polling or a C polling, the Z pollings are much easier to join because you just do that. Okay, it's much more easier. With the C pollings, like the one going around, it's much more difficult because you can't do something like this. You can't lap them. So what happens mostly, the Z pollings are more popular to use because it uses less material and it's more efficient as well than the C polling, which I will explain now. Okay, so when you join them, as you can see, if you're on site as a manager working for Quanstruct, one of these builders like Frasers, who does most of these, make sure the connection always sits over the rafter. Where you join them, I've got my rafter, I've got my joint here. Always make sure that joint sits over the rafter. Always. Okay? So that's what that slide there is saying, and it shows you how to join and lap them, which is what I've just shown. Okay, and this is the cleat. So that's the cleat which comes off this. So at the back of this, you'll have a cleat plate. So that's a cleat plate, which so with innovation these days, everything is becoming stronger. We've got now what we call Super Zs and Super Cs. So Super Zs are much more stronger than what you have a standard C or a normal Z. So this is a normal Z. You'll have Super Zs which have got ribs in them. So you've got ribs. So you can see the ribs there, these ones. So those ribs make them much stronger and they can take more load, in other words. So you can see here, for example, you have a 150 by 15 and the 200 by 15. So as I said, 150, 15, 150 is the depth. So that's the depth. And the wall thickness is the last two letters usually, if that makes sense. And this is the chart which tells you how many bridgings you can use. So if I have the span is 6 meters, okay, I have to use 2 rows of bridgings. So when you go to site, you will see this. So you will see every bay between the portal frames, they have got bridgings for the pollings. Similarly as well, you've got bridging as well for the wall cladding as well. Because the portal frame, so if I have one portal frame here, as I said, column, rafter, I have another one in the middle there, I've got the guards going this way horizontally. Is that correct? Which I showed before. So to prevent the guards from one portal frame to the next portal frame from sagging down, you then have bridging holding them in the middle. Does that make sense? That's how the bridging, so you have bridging for the wall and you'll have bridging as well for the roof polling. So the guards will have bridging and the roof pollings as well will have bridging. So sometimes when you want to save the bridging, because the bridging is not just expensive, it's manually done, so it's expensive overall. So usually most builders will go towards Super Z, which might maybe use just one bridging, rather than having 2 rows of bridging. So this is just showing you different spans, which I've already explained. You've got 3 spans. The first span will be the end span, internal span, and end span. This has got an end span and an end span. It's a simple span there, single span. And when you lap, you have to lap always over the support. That's very important. Okay? So these are just some tables showing you here. When you have, as I said, Z100, 10, which means the depth is 100 and the wall BMT is 1.0. Okay? It tells you how many bridging you need for different spans. So that's what that is telling you. So if that span is that much, the capacity when you have one bridging is, say if I take three, let me find something that is different. They're all the same here. 0. This, they're all the same. They are very little. Let me go to the next one and see. Okay, I will compare 1 and 3 bridging. So let's take 1 and 3 bridging. So the bridging span, this case is about 1.5 meters. This is not up to 2 meters, is it? Yeah, this is about 1.2 meters, which is not given here. So assuming the bridging length, the bridging span is 3 meters, or say, which one is different?
6,000.
They're all the same. Let me move to this next table. Yeah, here. So assuming, let's look at the, which one? 3 meters. They're the same. They are the same. I saw one that was different before. 1, 1, 1, 3. All right, I'll just explain what this table is saying. The span is 3 meters, for example. You have, if you have no bridging, okay, you see it takes that much load. If you have one bridging, it takes almost the same line load, which is the inward capacity. So the inward capacity is the one coming inwards. So that's the load, tells you if you have a roofing sheet, how much load each of the rafters can take when they have, sorry, not the rafters, the purlins can take when they have bridging. So that's for the Lysat purlins, okay? So if you have, I was looking for one that is different. Maybe when they go deeper, they are different. They're mostly the same. So what this is saying basically is bridging span, the type of purlins you're using. So if you're using 100, 100, 1.2, 100, 1.5, what happens is you can have different capacities, which is the inward capacity, for different purlins based on the number of bridging you provide. That's what that table is saying basically, which mostly will be used by an engineer. But as I said, most of the time, if you end up, like there is a student now, which is I think second year, working for Quanstruct, who does this. And he said he's lucky he did commercial construction. Otherwise, he wouldn't know anything what to do. What's the time? Got more time? Oh, we got a lot of time. Okay? And then this is the outward capacity. So, okay, this is different. So you see what I'm trying to say here. So it's for the same. The previous one was for the inward capacity. As I said, inward is the load outside pushing in, and outward is the load from internal pressure, from wind pushing out. Okay? So if you have, say, I'm looking at to the outward capacity, it means that purling capacity there, if I have a span of 4 meters, if there is no bridging provided, you see how much load I can take? 0.43. If I have one bridging, I can take 0.95. If I have 2 or 3 bridging, I can take 1.13 line load. So why that is important? Because it tells you if you want to have certain span, how much bridging you need to put in that span, and how much load you can take. So that will depend on the roofing cladding you're using for the inward capacity, and this will influence the capacity of the purlin when you're pushing outwards.
So if there's no difference, why would you put one?
Well, I didn't think that earlier on. Because outside it's a uniform load, when you have the roofing sheet moving out inwards, it's a uniform load. That's why most of the tables are the same, for 0, 1, or 2, or 3. Whereas inwards, you don't know where the pressure is going to be. That is why you'll have different capacities here. Okay? Now, when we do our purlins, it is very, very important to understand this element. When you do purlins, the purlins behave differently. They give you different capacities on how they are used. So what that means, it means you can have the purlin in front of the cleat, behind the cleat. So this is behind the cleat, this is in front of the cleat at the back. So the fall, so it means that this is the purlin, the rafter, it slopes this way. So it's exaggerated like that. And this rafter, I'm tired now, I think. This purlin can be like this, or it can be like this. How it's been used or how it's rotated is very, very important. Importantly, what you should know is, I'll take my rafter again. My rafter is that the top flange of either a C or a Z section should always point towards the apex. So that's my slope, like that. The best way to fix a Z purlin is like this, because that's the apex in the middle there. The reason being, if you put it like that, you have what we refer to as eccentric load. Because why? The Z purlin shear center is different when you put it this way. The load transfer is different from when you put it this way. And the best way to put the Z purlin or a C purlin is to ensure the top flange, that top flange faces towards the apex, which is the top middle part of the building, which is basically like the ridge in the normal domestic building. Okay? So what are some of the problems you get? What is this? What are some of the problems you get? So see, if you put, now these are just normal problems. I will explain what I've just said in the next slide. If you put the C purlin on the I side, of course, it's very, very easy to build because you've got a cleat. The cleat plate is already welded to the rafter when it comes to site. You just put it and it sits there. But what will happen is you'll have a lot of dust sitting in there, is it? Because, why is the C channel? Has it gone past? Why is it? Please don't take that home. You finish? Why is it always sitting with you? Have you guys seen it? Thank you. So as I'm saying, what happens is if you have your column, so I have my column sitting here, I have my rafter like that. If it sits like this, which is the first one, number one, then you'll have, it sits like this, it slopes like that. You'll have a lot of dust sitting here. Whereas if it sits like this, while dust will sit there, it's almost can clean itself when you have wind. Okay? Not much mess will be sitting at the back there. So that's what that slide is saying. So that one is easy to clean out. This is difficult to clean out. And the same thing as well for the Z purlin. When it turns that way, it's difficult to clean out. And when it turns that way, it's easy to clean out. But at the same time, it's easy to construct when it's like this, but difficult to construct when it's like this. Because these ones have to be bolted to the cleat plate. Similarly for the guts as well, when it's like that, it's easy. Okay, so usually when you have, if you go to a Bunnings, sometimes you just hear some click, 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 click sound behind the, it's very, very funny. It's happens recently. You have some funny sound behind the guts. Maybe the mouse, they are running and making some games. So if you have a column, if you put it like this, so that's how it will be fixed. So the column, okay? You know, an animal will just create a very good house at the back there without you knowing what's going on. Can have so many things happening behind there. Is that correct? But if it's like this, none of that will happen. So there is an advantage and disadvantage with the two. So that's what that is saying. So if you have it normally like that, there is no mouse runs, whereas like this, you'll have maybe a mouse, you can have the cockroaches, you can have so many things happening behind there which you will not see. Whereas like this as well, it's easy to clean, no mouse will hide there, whereas that one is difficult as well. Now this is the slide I was talking about before. It's a very important point to know how to rotate your purlins. Now, when you have, do you remember the word centroid from Materials and Structures? Center of gravity, remember that? Where the load goes through when you load a member. You remember that? Is that familiar to everyone? So the centroid of a section, 4 a Z section, the centroid is exactly at the middle there. So when you apply load to that member, you put a load there, that load will find a way and goes through the centroid. That's what you've learned in materials and structures. So for a C-section, the shear center is somewhere in there, and the centroid is somewhere there. So now when you look at this, what happens is, if you apply load onto a C-section, the line of action is vertical. So that line there is the same line here. Okay? What happens is, because the load has to act relative to the centroid or the shear center, if you push the load away from the the centroid, then it will sort of create a bigger moment. Is that correct? Or no? So what I'm saying, the shear center is somewhere here, okay, at the back of the section. When you apply load, that load will initiate bending about that shear center, which sits at the back of the section. So the closer the load is applied to the shear center, the better. The farther away it is, it's the bigger the moment, because the moment is forced by the distance. Is that correct? So if the shear center is closer to the load or the line of action of the load, then that makes it better. So what is happening here is, if you put the C-section this way, the eccentricity, which is the distance from the line of action from the shear center, is really small. Whereas if you put it this way, because you apply the load at the top when you screw it to the roofing sheet, if you put that load at the top, you see the E is bigger, because that E, that line will tend to provide bending about this point. Does that make sense? And this is something you should have done in materials and structures, by the way. This is very, very straightforward. So what we are trying to do is to ensure that that E is smaller, becomes small as possible. So that is why if you see the Z section, for example, because the shear center and the centroid is there, when you put the load at the top like that, because the slope is like this, it falls this way, it goes as much as possible and it generates smallest moment ever possible when it's that way. And that is why, and the reason why we say putting the C or Z section in which the top flange faces the apex is the best possible way. Does that make sense? And that is actually explained somewhere in one of those notes there. Okay? So the bridging in construction, as I said, is installed to all the purlins and the guts, and usually, it's in a straight line. So the bridging in a section, it does few things, which I think I already explained. One is it increases the outward capacity. So when you have a section like this, because this forms like a beam, it's from one portal frame to the next portal frame. It sits like that. It's likely to bend this way. Is that correct? So if you have the bridging, then that increases the capacity. So that is why there it says that it increases the member capacity. And as well, it restricts what we refer to as, so if you have a section like that, that moment there, or bending action there, is called out of plane. So this is not, I will take my phone. If I have a phone, okay, if I have a phone or a wall, assume this is a wall, okay, if I apply wind, that action is referred to as an out-of-plane action. And this action is referred to as an in-plane action. Is that correct? Did you learn that in materials? No. Of course not. So, when you have your purlin sitting on my 5 portal frames again, if I have bridging in, so, my God. If I have bridgings, what that bridging helps as well is to restrict the out-of-plane bending. So that's what that is saying there. Restrict out-of-plane movement. So I'm trying to explain that what that out of plane is, for those of you who don't understand that. In place, the other one I explained, that goes this way, perpendicular to the out of plane. Okay? So bridging comes in different configuration. They will look like that. You will have what we call herringbone, but it's very, very difficult to do. It's not popular anymore. Or you'll have a solid blocking. This is a solid blocking. The herringbone one, which uses the rods, are not popular anymore. Some people do use them, but not as popular as the solid blocking, which is much more stiffer. It's easy to attach as well, as opposed to an herringbone blocking. So this is how the bridging works as a whole. So the bridging has to work as one unit on its own and ensure the load from the roof that they resist is taken to ground. And that is why the bridging goes like that. So you've got the purlins in the middle, purlins as it goes. So that's a purlin there, the purlin there, purlin there. All of that is connected, and it's connected to the bridging that is used on the guards as well. So everything has to work as one. So usually what happens, if the spans are very long, sometimes, or not sometimes, most cases, you need to have a turnbuckle. So a turnbuckle is that. So what that does is that will be sort of loose when it's been connected at the start, and then the turnbuckle is used to sort of, you rotate that and it's tighten it up. It's like tightening a screw. So you tighten it up when you rotate that bit in the middle, and it's called an adjustable bridging. So that's a turnbuckle there. When that is done, it ensures that that entire bridging works as one unit in tension, resisting the load applied to it. Yes?
Why girds facing upwards?
It's just a drawing. I didn't draw that.
It's the wrong drawing.
No, it's not. Now, for the wall, the upwards is just about screening. It's not about capacity. Upwards or downwards will be the same. Yes. In that case, you'll have a lot of dirt, a lot of animals sitting there, mouse running. You'll have the, sometimes, in dangerous, like bush areas, you'll have maybe snakes that goes into the building and things like this. So yeah, they can hide there without you knowing, easily. Okay? Oh, that's the last I got. Any question? Any questions? Any questions? What happened? Too much? Okay? Tired. So tomorrow we'll continue with this. Tomorrow I'll give you a brief on the assignment. And then, so please make sure you come to class tomorrow, because I'll talk to you about the assignment. And then we'll talk about the site visit and the assignment submission.
Maybe we'll come next one and like what are the money for.
Uniform, I was going to
Yeah, I thought about